Langchain GenAI chat models. Description: explain in detail. The Langchain GenAI chat models are a collection of large language models (LLMs) provided by Google AI, accessible through the Langchain library. These models offer a range of capabilities, including text generation, translation, summarization, and question answering, making them versatile for diverse NLP tasks. Inputs. Input 1. Explain in detail. Textual input in the form of strings or lists of strings. The input can be a question, a prompt, or a piece of text to be analyzed. Input 2. Explain in detail. Optional parameters like temperature, top, and top, which control the model's output generation behavior. These parameters allow for fine-tuning the model's creativity and coherence. Outputs. Output 1. Explain in detail. A string representing the generated text output of the LLM based on the input and parameters provided. Output 2. Explain in detail. An optional dictionary containing additional information, such as confidence scores or metadata, depending on the specific model and its implementation. Steps. Step 1. Explain in detail. The input text is processed and encoded into a numerical representation suitable for the LLM. Step 2. Explain in detail. The encoded input is passed to the LLM's internal architecture, which uses a complex network of neurons to process and generate the output. Metrics. Metric 1. Explain in detail. Perplexity, a measure of how well the model predicts the next word in a sequence. Lower perplexity indicates a better understanding of the language and context. Metric 2. Explain in detail. Blue score, a measure of the similarity between the generated output and a reference translation or summary, often used for evaluating machine translation systems. Visualization plots. Visualization plot 1. Explain in detail. Attention visualizations. These plots can show how the LLM focuses on different parts of the input text during its processing, providing insights into the model's reasoning. Visualization plot 2. Explain in detail. Embeddings plots visualizations of the numerical representations of words or phrases can reveal relationships and similarities between different concepts. Fine-tune parameters. Parameter 1. Explain in detail. Learning rate determines how quickly the model adjusts its parameters during training, impacting convergence speed and accuracy. Parameter 2. Explain in detail. Batch size controls the number of training examples processed in each iteration, affecting training efficiency and memory usage. Uncertainty methods. Uncertainty method 1. Explain in detail. Ensemble methods combining multiple models' predictions can provide a more robust and accurate estimate of the model's uncertainty. Uncertainty method 2. Explain in detail. Dropout, a technique that randomly removes neurons during training, forcing the model to learn more robust representations and reducing overfitting. Challenges and fixes. Challenge 1. Explain in detail. Bias in generated text. LLMs can perpetuate biases present in their training data, leading to biased or discriminatory outputs. Sample use case that resulted in challenge 1. A model trained on a dataset with predominantly male authors might generate text that perpetuates gender stereotypes. Fixes to challenge 1. Data debiasing. Preprocessing training data to mitigate biases by removing biased terms or balancing the representation of different groups. Bias mitigation techniques using algorithms specifically designed to address biases in pay models' outputs. Challenge 2. Explain in detail. Lack of context awareness. LLMs may struggle to maintain context across long conversations or when dealing with complex and nuanced language. Sample use case that resulted in challenge 2. A model might fail to understand the overall context of a conversation and generate responses that are irrelevant or inconsistent with the previous turns. Fixes to challenge 2 contextualized embeddings using representations that capture the relationships between words and their surrounding context, improving the model's ability to understand the flow of the conversation. Memory mechanisms, implementing mechanisms that allow the model to store and retrieve information from previous conversations, improving its ability to maintain context. Langchain Google GenAI chat models. Chat Google Generative AI. Description: the Chat Google Generative AI class from Langchain is a wrapper around Google's generative AI API. It allows users to interact with Google's powerful language models and access their capabilities within Langchain workflows. Inputs: prompt, a string containing the user's input, question, or request. Temperature, a float value controlling the randomness of the model's output. Higher values lead to more creative and unpredictable responses. Top, an integer specifying the number of top K tokens to consider during sampling. This parameter affects the diversity of the model's output. Top, a float value representing the probability threshold for nucleus sampling. It controls the diversity of the generated text by focusing on the most probable tokens. Max output, tokens, an integer limiting the maximum number of tokens generated by the model. Stop sequences, a list of strings that serve as stop sequences during text generation. When encountered, the model stops generating further text. Model, the name of the specific Google Generative AI model to be used. Outputs: text, the generated text response from the Google Generative AI model, containing the model's answer, summary, or other requested content. Steps: the Langchain library constructs a request to Google's Generative AI API, providing the user's input prompt and any additional parameters. The request is sent to the Google API, which utilizes the selected model to process the prompt and generate a text response. The response from the API is received by the Langchain Chat Google Generative AI class and returned to the user as the output text. Metrics: response quality evaluates the relevance, accuracy, and coherence of the generated text response to the user's input. Model performance assesses the model's efficiency and speed in generating responses, considering factors like latency and resource usage. Visualization plots: token distribution visualizes the distribution of tokens generated by the model, providing insights into the model's vocabulary and language usage. Fine-tune parameters: learning rate controls the step size during model training, impacting the convergence rate and the risk of overfitting. Epochs represents the number of passes through the training dataset, influencing the model's learning and overall performance. Batch size defines the number of training examples used in each iteration, affecting the training speed and memory usage. Uncertainty methods: temperature scaling, the temperature parameter influences the randomness of the model's output, allowing for exploration of different levels of uncertainty. Top K sampling: by specifying top, users can control the number of top K tokens considered, impacting the model's confidence in the selected tokens. Nucleus sampling: the top parameter allows for sampling from a nucleus of the most probable tokens, introducing a level of uncertainty in the output. Challenges and fixes: Challenge 1: long response times due to network latency or API request processing delays. Sample use case that resulted in Challenge 1: executing a query that requires a large amount of processing, such as generating a lengthy text summary. Fixes to Challenge 1: optimize network connectivity, use a more efficient Google Generative AI model, or implement caching strategies to reduce repeated API calls. Challenge 2: API rate limiting or quota restrictions. Sample use case that resulted in challenge 2 exceeding the allowed number of requests within a specified time period. Fixes to challenge 2 implement a rate limiter to enforce API usage within the defined limits. Or explore alternative solutions for large-scale generation tasks. Challenge 3 API authentication issues. Sample use case that resulted in challenge 3 incorrect or missing API keys or authorization credentials. Fixes to challenge 3 ensure correct configuration of API credentials, verify access permissions, and resolve any authentication errors. Challenge 4 limited model availability or version incompatibility. Sample use case that resulted in challenge 4 using an older version of the library or attempting to access a model that is not supported or available. Fixes to challenge 4 update Langchain library to the latest version. Refer to the official documentation for supported models. And use compatible Google generative AI models. Langchain Google GenAI chat models chat Google generative AI. Description: the chat Google generative AI is an exception raised by Langchain's chat Google generative AI model when there is an error during interaction with Google's generative AI service. Inputs: model name, the name of the Google generative AI model being used. Prompt: the user prompt sent to the model. API key: the Google Cloud Platform API key used for authentication. Temperature: the temperature parameter used for controlling the model's creativity. Top: the top P parameter used for controlling the diversity of the generated text. Top: the top K parameter used for controlling the number of tokens considered during generation. Max tokens: the maximum number of tokens allowed in the generated response. Outputs: message: a detailed error message explaining the reason for the failure. Code: an error code indicating the specific type of error encountered. Steps: the chat Google generative AI model sends the user prompt to Google's generative AI service. The Google AI service processes the prompt and attempts to generate a response. If an error occurs during the process, the service sends an error message back to the Langchain model. The Langchain model catches the error and raises a chat Google generative AI exception, including the error message and code. Metrics: latency: the time taken to process the request and generate a response. Error rate: the percentage of requests that result in errors. Visualization plots: none. Fine-tune parameters: none. Uncertainty methods: none. Challenges and fixes. Challenge 1: invalid API key or missing API key. Sample use case that resulted in challenge 1 calling the chat Google generative AI model without providing a valid API key or failing to properly set the API key in the environment. Fixes to challenge 1. Ensure that you have a valid Google Cloud Platform API key and that it is properly configured in your environment or passed as an argument to the chat Google generative AI model. Challenge 2: network connectivity issues. Sample use case that resulted in challenge 2: the system trying to interact with Google's generative AI service while having a poor or unstable internet connection. Fixes to challenge 2: verify your internet connection and ensure that it is stable and reliable. Consider using a VPN or proxy if you are behind a firewall or encountering network restrictions. Challenge 3: insufficient quota. Sample use case that resulted in challenge 3: attempting to generate text beyond the allowed quota for your Google Cloud Platform project. Fixes to challenge 3: check your Google Cloud Platform project's quota and ensure you have enough capacity to make a request. Increase your quota if necessary. Challenge 4: model unavailable or overloaded. Sample use case that resulted in challenge 4: attempting to interact with a Google generative AI model that is temporarily unavailable or experiencing high load. Fixes to challenge 4. Retry the request later, as the model may be experiencing temporary downtime. If the issue persists, consider using a different Google generative AI model. Challenge 5. Invalid prompt format. Sample use case that resulted in challenge 5 providing an invalid or malformed prompt to the model. Fixes to challenge 5. Review the prompt format and ensure it adheres to the model's specifications. Refer to the documentation for the specific model you are using to understand its expected prompt. Structure. Challenge 6. Rate limiting. Sample use case that resulted in challenge 6 exceeding the rate limit for requests to Google's generative AI service. Fixes to challenge 6. Implement a rate limiting strategy in your code to avoid sending requests too frequently. Consider using a queue or other mechanism to buffer requests and send them at a controlled pace. Challenge 7. API errors or service disruptions. Sample use case that resulted in challenge 7 encountering unexpected errors or service disruptions on Google's generative AI service side. Fixes to challenge 7. Check the status of Google's generative AI service for any reported outages or issues. Retry the request later if the issue appears to be temporary. Contact Google support if the issue persists or if you believe there may be a more fundamental problem. Langchain Google GenAI embeddings. Description. Explain in detail. This component leverages Google's AI platform to generate embeddings for text, enabling semantic understanding and efficient similarity search. Inputs. Input 1. Explain in detail text, a string containing the text you want to embed. Input 2. Explain in detail model A Google AI model e.g. text embedding ADA002 specialized for embedding generation. Outputs. Output 1. Explain in detail embeddings, a numerical representation of the input text, capturing its semantic meaning. The format depends on the chosen model. Steps. Step 1. Explain in detail tokenization. The input text is broken down into individual words or subwords. Step 2. Explain in detail embedding generation. The model processes the tokens and generates a corresponding vector representation for each token. These vectors are then combined to produce a single embedding for the entire text. Metrics. Metric 1. Explain in detail embedding similarity. Measures the cosine similarity between two embeddings to assess their semantic relatedness. Metric 2. Explain in detail dimensionality. The number of elements in the embedding vector, which can influence the model's complexity and performance. Visualization plots. Visualization plot 1. Explain in detail embedding visualization plots. Embeddings in lower dimensional space to visualize their relationships and clusters. This can be done using techniques like T-SNE or PCA. Fine-tune parameters. Parameter 1. Explain in detail model selecting a specific Google AI model for embedding generation can impact the quality and performance. Uncertainty methods. Uncertainty method 1. Explain in detail confidence scores. Some Google AI models provide confidence scores for their predictions, indicating the model's certainty in its embedding. Uncertainty method 2. Explain in detail ensemble methods. Combining predictions from multiple models can help reduce uncertainty and improve overall performance. Challenges and fixes. Challenge 1. Explain in detail model selection. Choosing the right Google AI model for embedding generation can be challenging, as different models have varying strengths and weaknesses. Sample use case that resulted in challenge 1. Using a model designed for general text embedding on specialized domain-specific text might lead to suboptimal performance. Fixes to challenge 1. Experiment with different models and evaluate their performance on your specific dataset to identify the best option. Challenge 2. Explain in detail dimensionality reduction. Reducing the dimensionality of embeddings can be crucial for efficiency and visualization, but it can also lead to information loss. Sample use case that resulted in Challenge 2 using a high-dimensional embedding for similarity search might be computationally expensive, and reducing dimensionality can compromise semantic accuracy. Fixes to Challenge 2. Carefully select a dimensionality reduction technique, e.g. PCA, tsna, and adjust parameters based on the trade-off between efficiency and information preservation. Langchain Google GenAI embeddings. Google Generative AI embeddings. Description: the Google Generative AI embeddings class from Langchain is a powerful tool for generating embeddings of text using Google's generative AI models. These embeddings capture the semantic meaning of text, making them ideal for various downstream tasks like similarity search, clustering, and classification. Inputs: text. The input text for which you want to generate an embedding. This can be a single string or a list of strings. Model: the name of the Google Generative AI model you want to use for embedding generation. The supported models may vary based on your Google Cloud project setup. Outputs: embeddings. A list of embedding vectors, where each vector represents the semantic meaning of the corresponding input text. The length of the output list will match the length of the input list. Each embedding is a numerical array of floats. Steps: text preprocessing. The input text is typically preprocessed to remove irrelevant characters, normalize white space, and possibly apply other transformations based on the chosen model. Embedding generation: the preprocessed text is then passed to the selected Google Generative AI model, which generates a numerical embedding vector representing the text's semantic meaning. Metrics: embedding quality. The quality of the generated embeddings can be assessed by evaluating their performance on downstream tasks like similarity search, where high-quality embeddings should result in accurate matching of semantically similar texts. Model efficiency: the speed and resource consumption of the embedding generation process can also be used to evaluate the efficiency of the chosen model. Visualization plots: embedding visualization. The generated embeddings can be visualized in low-dimensional space using techniques like tsna or PCA. This can help to understand the relationships between different texts based on their semantic similarity. Clustering plots: embeddings can be used to perform clustering, grouping similar texts together. Visualizing these clusters can provide insights into the underlying structure of the data. Fine-tune parameters. Model selection: the choice of the Google Generative AI model can significantly impact the quality and characteristics of the generated embeddings. Different models may excel at capturing specific aspects of meaning or have different computational requirements. Preprocessing options: experimenting with different text preprocessing techniques can fine-tune the input for the embedding generation process, potentially improving embedding quality. Uncertainty methods. Confidence scores: some generative AI models may provide confidence scores along with their generated embeddings, indicating the model's certainty about the generated representation. This can be helpful for downstream tasks where uncertainty estimation is important. Challenges and fixes. Challenge 1: model availability. The availability of specific Google Generative AI models may vary depending on your Google Cloud project configuration and permissions. Sample use case that resulted in Challenge 1: attempting to use a model that is not enabled in your project. Fixes to Challenge 1. Ensure that the desired model is enabled within your Google Cloud project. Check the documentation for the specific model and confirm its availability in your project. Challenge 2. API key configuration. Incorrectly configured API keys or missing permissions can prevent successful communication with the Google Generative AI service. Sample use case that resulted in challenge 2: using an invalid API key or failing to properly authenticate with the Google Cloud service. Fixes to challenge 2. Verify that you are using the correct API key. Ensure that the API key has sufficient permissions for using the Google Generative AI service. Consult the Google Cloud documentation for proper API key configuration and authentication. Procedures. Challenge 3. Resource constraints. Generating embeddings can be computationally intensive, especially for large amounts of text or complex models. This can lead to resource limitations. Sample use case that resulted in challenge 3: trying to generate embeddings for a large volume of text using a resource-intensive model on a system with limited resources. Fixes to challenge 3. Optimize the model selection to choose a less computationally demanding option. Process text in batches to reduce memory usage. Leverage Google Cloud resources like Cloud GPUs or TPUs for more efficient processing. Challenge 4. Text length limitations. Some generative AI models may have limitations on the length of text that can be processed at once. Sample use case that resulted in challenge 4: trying to generate an embedding for a very long document that exceeds the model's input length limit. Fixes to challenge 4. Break down the long text into smaller chunks that fit within the model's limitations. Generate embeddings for each chunk separately and then combine the resulting vectors if necessary. Explore models that have higher input length limits. Langchain Google GenAI. Description. Explain in detail. The GenAI tool in Langchain utilizes Google's AI platform to provide a robust and scalable solution for question answering. This tool seamlessly integrates with Google's text-to-text models, enabling it to understand and respond to user queries in a natural and informative way. By leveraging Google's AI infrastructure, GenAI offers efficient processing and reliable responses, making it a valuable asset for various question answering applications. Inputs. Input 1. Explain in detail. Query the user's question or query that the tool aims to answer. This input is a string representing the user's request for information. Input 2. Explain in detail. Context. Optional text that provides context for the question. This can be a document, a passage, or any relevant text that helps the tool understand the query and provide a more accurate answer. The context is a string containing the additional information. Outputs. Output 1. Explain in detail. Answer the generated response to the user's query. This output is a string containing the answer formulated by the GenAI tool based on the provided query and context. Output 2. Explain in detail. Confidence score. Optional, a numerical score representing the tool's confidence in the generated answer. This score provides insight into the quality and reliability of the response. Steps. Step 1. Explain in detail. Query processing. The GenAI tool first receives the user's query and processes it to extract relevant information and identify the user's intent. Step 2. Explain in detail. Context integration. If provided, the tool integrates the context with the query to enhance understanding and provide a more accurate answer. Step 3. Explain in detail. Model inference. The tool utilizes Google's text-to-text models to generate the answer. These models are trained on massive datasets and are capable of understanding and responding to a wide range of queries. Step 4. Explain in detail. Response generation. The generated answer is then returned to the user. Metrics. Metric 1. Explain in detail. Accuracy. Evaluates the correctness of the generated answer by comparing it to known ground truth responses. Metric 2. Explain in detail confidence if applicable measures the tool's confidence in a provided answer. This can be assessed through metrics like the confidence score or probability distribution. Visualization plots. Visualization plot 1. Explain in detail query answer visualization, a graphical representation of the user's query, context if provided, and the generated answer. This helps visualize the flow of information and understand how the tool processes the query. Fine-tune parameters. Parameter 1. Explain in detail model selection, choosing a specific Google AI platform model for text-to-text tasks. Different models may have varying strengths and weaknesses depending on the specific domain or task. Uncertainty methods. Uncertainty method 1. Explain in detail confidence score. If applicable, the tool can provide a confidence score to indicate its certainty in the generated answer. Higher scores represent greater confidence. Challenges and fixes. Challenge 1. Explain in detail unclear or ambiguous queries. Queries that are poorly phrased, lack context, or have multiple interpretations can lead to inaccurate or irrelevant responses. Sample use case that resulted in challenge 1. A user asks what is the capital of France, without providing any context, and the tool might provide an incorrect answer due to misinterpretation of the query. Fixes to challenge 1. Contextualization. Provide additional information to clarify the query and resolve ambiguity. Query refinement. Use techniques like query expansion or paraphrasing to rephrase the query for better understanding. Challenge 2. Explain in detail limited context. The tool may struggle to provide accurate answers when the provided context is insufficient or incomplete. Sample use case that resulted in challenge 2. A user asks what is the population of Paris, with limited context, and the tool may provide an inaccurate answer due to the lack of relevant information. Fixes to challenge 2. Context augmentation. Provide more context by supplementing the input text with relevant information from external sources or knowledge bases. Context extraction. Implement techniques to extract relevant information from the provided context or external sources to enrich the context for the query. Challenge 3. Explain in detail domain-specific knowledge. The tool may lack specialized knowledge in certain domains, leading to inaccurate or incomplete answers. Sample use case that resulted in challenge 3. A user asks what are the latest advancements in quantum computing, and the tool may provide an answer that is not entirely accurate or up to date due to its limited domain-specific knowledge. Fixes to challenge 3. Domain-specific models utilize Google AI platform models specifically trained for the desired domain. Knowledge integration. Integrate external knowledge bases or specialized resources that contain domain-specific information. YAML. Langchain Google GenAI का AQA input. Description. The AQA input class is a custom input class for the Google GenAI AQA model. It encapsulates the necessary information required for the model to perform question answering on a given context. Inputs. Question. The user's question that needs to be answered. Context. The text that provides the context for the question. This can be a document, article, or any other text source. Outputs. Answer. The generated answer to the question based on the provided context. Steps. The AQA input object is created with the question and context as input. The object is passed to the Google GenAI AQA model. The model processes the input and generates an answer based on the provided context. The answer is returned as the output. Metrics. Accuracy. The percentage of correctly answered questions. F1 score, a measure of the model's ability to identify relevant information in the context and Provide accurate answers. Visualization plots. Attention visualization. A visualization of the model's attention weights during the answering process, highlighting the parts of the context that were most relevant to the question. Fine-tune parameters. Learning rate controls the step size during model training. Batch size. The number of samples processed at once during training. Uncertainty methods. Temperature scaling adjusts the model's confidence in its predictions by introducing randomness. Dropout. Randomly drops out neurons during training to prevent overfitting. Challenges and fixes. Challenge 1. The model may struggle to answer questions that require reasoning or inference beyond the explicit information provided in the context. Sample use case that resulted in Challenge 1. A question asking for the author's opinion on a topic, where the context only provides factual information about the topic. Fixes to Challenge 1. Train the model on a dataset that includes questions requiring reasoning and inference. Use a larger language model with improved reasoning abilities. Challenge 2. The model may generate incorrect or irrelevant answers if the context contains ambiguous or contradictory information. Sample use case that resulted in Challenge 2. A question about a historical event where the context provides conflicting accounts from different sources. Fixes to Challenge 2. Use a more reliable and consistent source for the context. Train the model on a dataset that includes diverse and challenging contexts. YAML. Langchain Google GenAI का AQA output. Description. The AQA output class represents the output of a question answering model in Langchain. It provides a structured way to store and access information related to the model's response, including the answer itself, the reasoning behind it, and any relevant context or supporting evidence. This class is specifically designed for Google's generative AI models. Inputs. Question. The question asked by the user. It's the primary input that drives the question answering process. Context. The context provided to the model. It could be a document, text, or a set of documents that the model uses to find the answer to the question. Outputs. Answer. The answer generated by the model in response to the question. It's the core output of the question answering process. Reasoning and explanation of how the model arrived at the answer. It helps understand the model's thought process and reasoning behind its answer. Steps. Question. Understanding the model first analyzes the question to identify the key entities, relationships, and intent. Context retrieval. Based on the question understanding, the model retrieves relevant information from the provided context. Answer generation. The model generates an answer by combining the understanding of the question with the retrieved information from the context. Reasoning generation. The model provides a textual explanation of its reasoning process, highlighting the key pieces of information from the context that supported its answer. Metrics. Accuracy. This metric evaluates the correctness of the generated answer. It measures how closely the answer aligns with the actual information in the context. Coherence. This metric assesses the quality and flow of the generated answer. It checks if the answer is well structured, coherent, and easy to understand. Relevance. This metric measures the relevance of the generated answer to the question asked. It ensures that the answer addresses the question directly and does not provide irrelevant or extraneous information. Visualization plots. Attention heat map. This plot visualizes the attention weights assigned by the model to different words in the context during answer generation. This helps understand which parts of the context were most important for arriving at the answer. Reasoning graph. This graph represents the reasoning process of the model, showing how different pieces of information in the context are connected to form the answer. Fine-tune parameters. Temperature. This parameter controls the randomness of the generated answer. Higher values lead to more creative and unexpected answers, while lower values result in more consistent and predictable answers. Top K. This parameter limits the number of potential words that the model considers during answer generation. It helps focus the model on generating answers that are more relevant and coherent. Uncertainty methods. Confidence score. The model can generate a confidence score for its answer, indicating its level of certainty in the generated response. Uncertainty range. The model can provide a range of possible answers, reflecting the uncertainty associated with the answer. This helps users understand the potential variations and limitations of the model's prediction. Challenges and fixes. Challenge 1. Hallucination. The model may generate incorrect or fabricated information not present in the provided context. Sample use case that resulted in challenge 1. The model was asked a question about a historical event, and it generated an answer that included details that were not true. Fixes to challenge 1. Use a model with better fact-checking capabilities. Provide more context and relevant information to the model to reduce the chances of hallucination. Challenge 2. Bias. The model may exhibit biases in its answers, reflecting the biases present in its training data. Sample use case that resulted in challenge 2. The model was asked a question about a particular profession, and it generated an answer that stereotyped the profession based on gender or race. Fixes to challenge 2. Use a model trained on a more diverse and unbiased dataset. Provide explicit instructions to the model to avoid biased language and responses. Challenge 3. Lack of contextual understanding. The model may struggle to understand the context of the question and generate answers that are not relevant or coherent. Sample use case that resulted in challenge 3. The model was asked a question about a specific event, but it generated an answer that was completely unrelated to the event. Fixes to challenge 3. Provide more context and relevant information to the model. Use a model with better contextual understanding capabilities. Langchain Google GenAI. Description. Explain in detail. GenAI is a Langchain tool that leverages Google's generative AI GenAI capabilities to answer questions. It utilizes the Google AI platform's text-to-text model, specifically fine-tuned for question answering tasks. This allows GenAI to process user queries and retrieve relevant information from a provided context or document. The tool is designed to deliver comprehensive and insightful responses based on the given information. Inputs. Input 1. Explain in detail query, the question that the user wants to ask. This input is a string representing the user's query. Input 2. Explain in detail context, the document or text containing the information needed to answer the query. This input can be a string, a list of strings, or a document. Outputs. Output 1. Explain in detail answer, the answer to the user's question based on the provided context. This output is a string containing the generated answer. Output 2. Explain in detail source documents, if the context is a list of documents. This output will contain the specific documents used to generate the answer. This is a list of strings representing the source documents. Steps. Step 1. Explain in detail. The GenAI tool first receives the user's query and the context. Step 2. Explain in detail. The query and context are then sent to the Google AI platform's text-to-text model. This model is specialized for question answering, enabling it to analyze the provided context and identify the relevant information to answer the Query. Step 3. Explain in detail based on the analysis of the context and the query. The model generates a comprehensive and informative answer. Step 4. Explain in detail. The tool returns the generated answer to the user. Metrics. Metric 1. Explain in detail accuracy. This metric assesses how accurately the tool provides answers to user queries based on the given context. Accuracy can be measured by comparing the generated answers to human-evaluated answers or to a ground truth dataset. Metric 2. Explain in detail coherence. This metric measures the quality and clarity of the generated answers. It evaluates whether the answers are grammatically correct, logically sound, and coherent with the provided context. Visualization plots. Visualization plot 1. Explain in detail answer length distribution. This plot shows the distribution of the lengths of the generated answers. It can be used to identify patterns in answer length and assess whether the model is generating answers that are too short or too long. Visualization plot 2. Explain in detail answer vs. context length. This plot compares the length of the generated answers to the length of the provided context. This can help understand the relationship between context length and answer length and identify potential issues related to overly short or long answers. Fine-tune parameters. Parameter 1. Explain in detail temperature. Controls the randomness of the model's output. Higher temperatures result in more diverse and creative answers, while lower temperatures produce more deterministic and predictable answers. Parameter 2. Explain in detail top. This parameter influences the selection of the most likely words during the generation process. A higher top value results in a wider selection of words, while a lower value limits the choice to the most likely words. Uncertainty methods. Uncertainty method 1. Explain in detail confidence score. The model can provide a confidence score for each generated answer. This score indicates the model's level of certainty about the accuracy of the answer. Higher scores represent higher confidence, while lower scores suggest potential uncertainty. Uncertainty method 2. Explain in detail entropy. This metric measures the randomness of the model's predictions. Higher entropy indicates more uncertainty in the model's output, while lower entropy suggests higher confidence in the generated answer. Challenges and fixes. Challenge 1. Explain in detail context understanding. If the context is complex or ambiguous, the model might struggle to accurately understand the meaning and extract the relevant information. Sample use case that resulted in challenge 1. The context contains multiple entities with similar names, making it difficult for the model to distinguish between them. Fixes to challenge 1. To address this, one can try providing more context-specific information or using techniques like named entity recognition to help the model better understand the context. Challenge 2. Explain in detail bias in the training data. If the training data used to fine-tune the model contains biases, these biases might reflect in the generated answers. Sample use case that resulted in challenge 2. The training data is biased towards a specific gender or ethnicity, leading to biased answers when asked questions about sensitive topics. Fixes to challenge 2. It is important to use balanced and diverse training data to mitigate bias in the model's outputs. One can also explore techniques like fairness-aware training to further reduce biases in the model. Challenge 3. Explain in detail hallucination. The model might generate answers that are not supported by the provided context or that contain inaccurate information. Sample use case that resulted in challenge 3. The user asks a question about a specific event, and the model generates an answer that includes details about a similar but different event. Fixes to challenge 3 techniques like fact-checking and using external knowledge sources can be employed to verify the accuracy of the generated answers and reduce the risk of hallucinations. Langchain Google GenAI Google Vector Store. Description: explain in detail. The Google Vector Store component in Langchain is a specialized vector store that leverages Google's Vertex AI embedding service to store and retrieve vector representations of your data. It enables efficient similarity search and retrieval of documents or data points based on their semantic meaning. Inputs. Input 1. Explain in detail text data. You provide text data, documents, articles, etc. that you want to embed and store. This data can be in various formats, such as plain text, Markdown, or HTML. Input 2. Explain in detail embedding model. This is the Google Vertex AI embedding model that you want to use for creating vector representations of your data. Google offers a range of pre-trained embedding models, each specialized for different tasks and domains. Outputs. Output 1. Explain in detail embedded vectors. The component generates vector representations of your input text data using the specified embedding model. These vectors are numerical representations of the semantic meaning of your data. Output 2. Explain in detail vector store. These vectors are then stored in a scalable and efficient vector store managed by Google Vertex AI. Steps. Step 1. Explain in detail data preprocessing. The input text data is typically preprocessed to prepare it for embedding. This may involve steps like removing stop words, stemming or lemmatization, and tokenization. Step 2. Explain in detail embedding. The preprocessed text data is fed into the selected Google Vertex AI embedding model, which generates numerical vector representations for each piece of text. Step 3. Explain in detail vector store storage. The resulting vectors are stored in a Google Vertex AI vector store. This store is designed to handle large datasets efficiently and provides optimized indexing and search capabilities. Metrics. Metric 1. Explain in detail similarity search performance. One key metric is how efficiently a vector store can retrieve similar documents or data points based on queries. This is measured by factors like search latency, how fast results are returned, and recall percentage of relevant documents retrieved. Metric 2. Explain in detail embedding quality. The quality of the embedding model used directly impacts the accuracy of similarity searches. Metrics like perplexity and accuracy on downstream tasks can assess the quality of the generated vectors. Visualization plots. Visualization plot 1. Explain in detail vector space visualization. You can visualize the relationships between different vectors in the store using techniques like T-SNE or UMAP. This allows you to visually inspect how the embedding model has captured the semantic relationships in your data. Visualization plot 2. Explain in detail retrieval performance plots. You can plot metrics like precision, recall, and F1 score to visualize the performance of the vector store in retrieving relevant documents based on different query types. Fine-tune parameters. Parameter 1. Explain in detail embedding model parameters. Different embedding models have their own tunable parameters that influence the quality of the generated vectors. These can include parameters related to the model architecture, training data, and optimization settings. Parameter 2. Explain in detail vector store configuration. The vector store itself can have configuration parameters, such as the dimensionality of the vectors, the indexing strategy, and the search algorithm used. Tuning these parameters can impact search efficiency and performance. Uncertainty methods. Uncertainty method 1. Explain in detail confidence scores. Many embedding models can provide confidence scores or probabilities associated with the generated vectors. These scores can be used to assess the reliability of retrieved results and indicate when the model is uncertain about its predictions. Uncertainty method. To explain in detail ensemble methods, you can use ensemble methods with multiple embedding models to reduce uncertainty. By combining the predictions from different models, you can mitigate the impact of individual model biases and improve the robustness of the system. Challenges and fixes. Challenge 1. Explain in detail data scalability. Handling large datasets of text data can pose challenges for both embedding and storage. Sample use case that resulted in Challenge 1. Processing terabytes of text documents from a large corpus of scientific papers. Fixes to Challenge 1. Utilize Google Vertex's distributed processing capabilities for efficient parallel embedding of large datasets. Optimize the vector store configuration to handle large-scale data efficiently. Explore techniques like data sharding or distributed vector storage to manage the scale of data. Challenge 2. Explain in detail embedding quality and domain specificity. The choice of embedding model is crucial. If the model isn't well suited to the domain of your data, the embeddings might not accurately capture the semantic relationships. Sample use case that resulted in Challenge 2. Using a general-purpose embedding model for a highly specialized domain like medical literature. Fixes to Challenge 2. Carefully evaluate different embedding models based on their suitability for your specific domain. Consider fine-tuning a pre-trained model on a dataset relevant to your domain to improve its accuracy. Explore domain-specific embedding models offered by Google or other providers. Challenge 3. Explain in detail query formulation. Creating effective queries for similarity search can be challenging, especially for complex or nuanced search requests. Sample use case that resulted in Challenge 3. Trying to retrieve documents that are semantically similar to a query that is phrased in a complex or ambiguous way. Fixes to Challenge 3. Experiment with different query formats and representations. Use query expansion techniques to broaden the scope of the search. Consider incorporating external knowledge sources or domain expertise to improve query understanding. Challenge 4. Explain in detail resource management. Running embedding models and managing vector stores can be computationally expensive. Sample use case that resulted in Challenge 4. A high volume of search requests leads to increased computational costs associated with embedding and retrieval. Fixes to Challenge 4. Optimize the embedding process for efficiency. Use cost-effective embedding models and vector store configurations. Explore techniques like caching or indexing to reduce the computational load for repeated searches. Langchain Google GenAI Google Vector Store does not exist exception. Description: the does not exist exception is raised when a Google Vertex AI vector store does not exist in the given project and region. This exception is a subclass of Google APACO exceptions, not found, and is part of a Google Cloud AI platform GAPAC exceptions module. Inputs: Project ID, the Google Cloud Project ID where the vector store is expected to reside. Region: the Google Cloud region where the vector store is expected to be located. Vector store name: the name of the vector store being accessed. Outputs: Error message, a detailed message indicating the vector store does not exist, including project ID, region, and vector store name. Steps: The Langchain component attempts to access the specified Google Vertex AI vector store. The Google Cloud API Vertex AI is called to retrieve information about the vector store. The API call returns a Google APACO exceptions not found error. indicating the vector store does not exist. The does not exists exception is raised, encapsulating the error message received from the API. Metrics. API call latency, the time taken for the API call to retrieve information about the vector store. API call success rate, the percentage of successful API calls made to retrieve vector store information. Visualization plots. NA. Fine-tune parameters. NA. Uncertainty methods. NA. Challenges and fixes. Challenge 1. Incorrect project ID or region. The user might have specified an incorrect project ID or region, causing the API call to fail. Sample use case that resulted in challenge 1. A user tries to access a vector store in GCP PROJECT1 and US Central 1, but the vector store actually exists in GCP PROJECT2 and US East 1. Fixes to challenge 1. Double-check the project ID and region in the code or configuration settings to ensure they match the actual location of the vector store. Challenge 2. Misspelled vector store name. The user might have misspelled the vector store name during access, leading to the error. Sample use case that resulted in challenge 2. A user attempts to access a vector store named My Vector Store, but the actual name is My Vector Store Data. Fixes to challenge 2. Verify that the vector store name is correctly spelled in the code bar. Configuration settings. Challenge 3. Missing vector store creation. The vector store might not have been created in a specified project and region yet. Sample use case that resulted in challenge 3. A user attempts to access a vector store that is being created but not yet fully provisioned. Fixes to challenge 3. Ensure that the vector store has been successfully created in the Google Cloud project and region before attempting to access it. Wait for the creation process to complete. Langchain Google GenAI Google Vector Store. Google Vector Store description. The Google Vector Store class from Langchain's Langchain Google GenAI module is a specialized vector store designed to leverage Google's AI capabilities for efficient semantic search and retrieval. It uses Google's Vertex AI platform to create embeddings for text data, which are then stored and queried using the Google Vertex AI API. This allows users to perform similarity searches on large datasets, enabling applications like question answering, document retrieval, and recommendation systems. Inputs. Text data. This is the input text that will be used to create embeddings and populate the vector store. It can be a list of strings, a file path, or any other format that can be converted into a list of text documents. Google Cloud Project ID. This is the ID of the Google Cloud project where the Vertex AI service is configured. Google Cloud Region. This specifies the geographical region where the Vertex AI service is located. Embedding model. You need to select a pre-trained embedding model from Google's Vertex AI service. This model will be responsible for generating the numerical representations embeddings of your text data. Optional parameters. Additional parameters can be provided, such as embedding dim, embedding dimension, batch size, number of documents processed in one batch, and verbose control the level of logging. Outputs. Embeddings. The Google Vector Store generates numerical embeddings for each input text document. These embeddings capture the semantic meaning of the text and are used for similarity searches. Similarity scores. When querying the vector store, it returns a list of similar documents along with their associated similarity scores. These scores indicate the degree of semantic similarity between the query and each retrieved document. Steps. Data preparation. The input text data is processed and prepared for embedding generation. This may involve tokenization, cleaning, or other necessary pre-processing steps. Embedding generation. Google's Vertex AI service is used to generate embeddings for each text document. The selected embedding model is applied to the processed data, resulting in numerical representations. Vector store creation. The generated embeddings are stored in a vector store, allowing efficient similarity searches. The Google Vertex AI API handles the storage and retrieval operations. Querying. When a query is provided, the Google Vector Store generates an embedding for the query using the same embedding model. It then performs a similarity search within the vector store, retrieving documents that are most similar to the query based on their embedding representations. Results. The search results are returned as a list of documents along with their associated similarity scores. The documents are ranked based on their similarity to the query. Metrics. Embedding quality. The quality of the generated embeddings is crucial for effective similarity searches. This can be evaluated by measuring metrics like accuracy, precision, and recall on a benchmark dataset. Search efficiency. The efficiency of the vector store is determined by how quickly it can process queries and return results. This can be measured by factors like query latency and throughput. Visualization plots. Embedding visualization. Embeddings can be visualized in a low-dimensional space using techniques like tsna or PCA. This can help understand the semantic relationships between different documents. Similarity matrix. A similarity matrix can be created to visualize the pairwise similarity between all documents in the vector store. This can reveal clusters of similar documents. Fine-tune parameters. Embedding model selection. Choosing the right embedding model for your data is crucial for accurate similarity searches. You can experiment with different models from Google's Vertex AI service to find the best one for your specific use case. Embedding dimension. The embedding dimension controls the complexity of the embeddings. A higher dimension can capture more nuanced semantic information but may require more computational resources. Batch size. The batch size controls the number of documents processed at once. A larger batch size can speed up embedding generation but may require more memory. Uncertainty methods. Confidence scores. The Google Vector Store can provide confidence scores for each retrieved document, indicating the level of certainty in the similarity score. Ensemble methods. Using multiple embedding models and combining their predictions can help reduce uncertainty and improve robustness. Challenges and fixes. Challenge 1. Latency and throughput issues. Using Google's Vertex AI API for embedding generation and storage may introduce latency, especially for large datasets. This can impact the performance of similarity searches. Sample use case that resulted in challenge 1. When searching for similar documents in a large corpus of legal documents, the query response time was significantly delayed. Fixes to challenge 1. Optimize the query. Use more specific search terms or keywords to narrow down the search space and reduce the number of documents to process. Caching. Implement a caching layer to store frequently accessed embeddings and reduce the number of API calls to Vertex AI. Batch processing. Process large datasets in batches to distribute the workload and reduce the impact of latency on individual queries. Challenge 2. Embedding model selection. Choosing the right embedding model for your data is crucial for effective similarity searches. An inappropriate model can lead to poor results. Sample use case that resulted in challenge 2. Using a generic embedding model for a specialized dataset of medical literature resulted in low-quality search results, as the model was not trained on domain-specific language. Fixes to challenge 2. Fine-tuning. Fine-tune a pre-trained embedding model on your specific dataset to improve its performance. Domain-specific models explore domain-specific embedding models, such as BioBERT for medical texts or LegalBERT for legal documents. Evaluate different embedding models on a representative subset of your data to select the best one for your use case. Langchain Google GenAI Google Vector Store Server-Side Embedding. Description: this technique involves using Google's server-side embedding capabilities to represent textual data as vectors. These vectors capture the semantic meaning of the text and allow for efficient similarity searches. Inputs: text data. This can be any form of text, such as documents, articles, or chat logs. Embedding model: this refers to a pre-trained model capable of generating vector representations of text. Google provides a range of such models, such as Text Embedding ADA 002 or Text Similarity DaVinci 001. Outputs: vector database, a database that stores the generated text embeddings. Queryable vector database, the vector database can be queried using other text inputs. The system compares the vector representation of the query text to the vectors in the database, finding the closest matches, i.e., semantically similar content. Steps: text preprocessing. The input text data is typically cleaned and preprocessed, e.g., removing punctuation, lower casing. Embedding generation: the chosen Google embedding model is used to convert each text input into a numerical vector. This process captures the semantic meaning of the text. Database storage: the generated vectors are stored in a vector database, e.g., Pinecone. FIS. This database allows for efficient similarity searches based on the vectors. Metrics: accuracy, the ability to retrieve relevant information based on semantic similarity. Retrieval time, the speed at which the vector database can perform searches. Visualization plots. Vector similarity plots, visualizations that display the relationships between vectors in a database. This can help understand the semantic connections between different texts. Fine-tune parameters. Embedding model: choosing a different embedding model can impact the accuracy and performance of the system. Database configuration: optimizing the database parameters, e.g., dimensionality. Distance metric can influence search efficiency and accuracy. Uncertainty methods. Confidence scores: the embedding models can often provide confidence scores for the generated vectors, indicating the reliability of the representation. Ensemble methods: combining the results of multiple embedding models can reduce uncertainty. Challenges and fixes. Challenge 1: data scaling. Handling large volumes of text data for embedding and storage can pose performance challenges. Sample use case that resulted in Challenge 1: processing a large data set of news articles, leading to long processing times and storage limitations. Fixes to Challenge 1: data partitioning. Break the dataset into smaller chunks for processing. Distributed systems utilize distributed database systems to handle large datasets. Challenge 2: model selection. Choosing the right embedding model for a specific task can be challenging. Sample use case that resulted in Challenge 2: selecting an embedding model for a technical document. Retrieval system. But the model struggles to capture the nuances of technical language. Fixes to Challenge 2. Experimentation: test different models to find the best fit for the specific domain. Fine-tuning. Fine-tune pre-trained embedding models on domain-specific datasets. Langchain Google GenAI LLMs. Description: explain in detail. Langchain Google GenAI LLMs leverage Google's powerful AI models, like Palm 2, to provide access to advanced language capabilities within the Langchain framework. This allows users to build sophisticated applications by integrating Google's generative AI models seamlessly. Inputs: Input 1. Explain in detail text prompts. Users provide textual input in the form of questions, instructions, or creative prompts. Input 2. Explain in detail contextual information. Optionally, users can provide additional context to guide the model's response, such as previous conversations or specific documents. Outputs. Output 1. Explain in detail generated text. The model produces text output based on the provided prompts and context. This output can be in various formats, including stories, summaries, translations, and code. Output 2. Explain in detail structured data. Depending on the model and prompt, the output can also be structured data, like lists, tables, or JSON objects. Steps. Step 1. Explain in detail prompt preparation. Users craft their prompts, ensuring clarity and specificity to guide the model effectively. Step 2. Explain in detail model invocation. Langchain handles the communication with Google's API, sending the prepared prompts to the chosen GenAI model. Step 3. Explain in detail response processing. The model's output is received and processed by Langchain, potentially undergoing further analysis or integration within the application. Metrics. Metric 1. Explain in detail model accuracy. Evaluation of the model's ability to generate correct and relevant information based on the input. Metric 2. Explain in detail model fluency. Assessment of the fluency and coherence of the generated text, evaluating its grammatical correctness and natural language style. Visualization plots. Visualization plot 1. Explain in detail textual output visualizations. Visualizing the generated text with features like word clouds, sentiment analysis, or topic extraction. Visualization plot 2. Explain in detail model performance graphs. Visualizing metrics like accuracy, fluency, or latency over time. Fine-tune parameters. Parameter 1. Explain in detail temperature. Controls the randomness and creativity of the models. Output. Lower values result in more predictable and deterministic responses, while higher values lead to more diverse and potentially surprising outputs. Parameter 2. Explain in detail top K and top. These parameters control the probability distribution used for sampling words during generation. Top K selects the top K most probable words, while top considers words with cumulative probabilities exceeding the threshold P. These parameters influence the diversity and quality of the generated text. Uncertainty methods. Uncertainty method 1. Explain in detail confidence scores. Google's models might provide confidence scores indicating their certainty about specific parts of the generated text. These scores can be used to identify potentially less reliable or uncertain segments. Uncertainty method 2. Explain in detail ensemble methods. Combining multiple models or running same model with different random seeds can provide insights into the model's uncertainty. Comparing the outputs of different runs can highlight potential inconsistencies and provide a measure of confidence. Challenges and fixes. Challenge 1. Explain in detail model biases. Google's models, like other large language models, can exhibit biases learned from the vast datasets they are trained on. These biases can manifest in the generated text, potentially leading to unfair or discriminatory outputs. Sample use case that resulted in Challenge 1. A prompt asking for a story about a scientist might disproportionately generate characters who are male or white, reflecting biases present in the training data. Fixes to Challenge 1. Pre-processing data. Removing biased content from the training data or using techniques like adversarial training to mitigate biases. Prompt engineering. Crafting prompts that explicitly address potential biases and encourage diverse and inclusive outputs. Post-processing using techniques like debiasing algorithms or human review to identify and correct biased outputs. Challenge 2. Explain in detail factual inaccuracies. Large language models can sometimes generate outputs containing factual errors or inconsistencies. These inaccuracies can arise from limitations in their training data or from the model's tendency to create plausible but incorrect information. Sample use case that resulted in challenge 2. A prompt asking for a summary of a historical event might contain factual inaccuracies about dates, locations, or participants. Fixes to challenge 2. Fact-checking using external knowledge sources or human review to verify the accuracy of generated text. Training on factual datasets including high-quality factual data in the training process to improve the model's ability to generate accurate information. Fine-tuning the model on specific domains or tasks to improve its accuracy in generating factual information related to those areas. Langchain Google GenAI LLMs Google Generative AI. Description. Explain in detail. The Google Generative AI LLM is a powerful tool for natural language processing tasks within Langchain. It allows you to leverage Google's advanced generative AI capabilities directly through the Langchain framework, offering seamless integration with Google Cloud services. Inputs. Input 1. Explain in detail. The primary input to the Google Generative AI LLM is the text prompt. This prompt is the core element that guides the model's generation process. It can be a simple question, a creative writing prompt, or any other text-based instruction. The prompt should be clear and concise to ensure that the model understands the desired output. Input 2. Explain in detail. An optional input is the temperature parameter. This parameter controls the randomness and creativity of the generated text. A higher temperature value will result in more diverse and unpredictable outputs, while a lower value will produce more conservative and predictable results. Outputs. Output 1. Explain in detail. The primary output is the generated text, which is the result of the model's processing of the input prompt. The generated text will be a response to the prompt, incorporating relevant information and adhering to the instructions provided. The quality and coherence of the generated text depend on the quality of the prompt and the capabilities of the underlying Google AI model. Output 2. Explain in detail. There might be additional outputs depending on the specific Google AI model used. For example, some models may provide confidence scores or other metadata related to the generated text. Steps. Step 1. Explain in detail. The first step involves sending the input prompt and any optional parameters to the Google Generative AI LLM. This is typically done through a dedicated API call. Step 2. Explain in detail. The LLM processes the prompt and generates the desired text output based on its training data and the provided parameters. Metrics. Metric 1. Explain in detail. The quality of the generated text is a key metric. It can be evaluated subjectively by humans or objectively using metrics like perplexity, Blue score, and Rouge score. These metrics assess the fluency, coherence, and relevance of the generated text compared to a reference or expected output. Metric 2. Explain in detail. The latency of the model, or the time it takes to process the prompt and generate the output, is another important metric. This is especially crucial in real-time applications where prompt responses need to be fast. Visualization plots. Visualization plot 1. Explain in detail. You could use visualization plots to represent the distribution of confidence scores or other metadata associated with the generated text. This can help to identify potential issues with the model's output or highlight areas where it Performs well. Visualization plot. To explain in detail a timeline plot could be used to visualize the latency of the model for different prompt lengths or complexities. This can help to understand how the model's performance scales with the input size and complexity. Fine-tune parameters. Parameter 1. Explain in detail. While direct fine-tuning of the underlying Google AI model is typically not available through the Langchain interface, you might have control over certain parameters like the temperature, top, and top, which can influence the model's behavior and output. Parameter 2. Explain in detail. The model might allow for setting a context window size. This determines how much previous text is considered when generating the output. A larger context window can improve the coherence of longer texts but might also increase latency. Uncertainty methods. Uncertainty method 1. Explain in detail. The Google Generative AI LLM may provide confidence scores associated with its output. This can be used to estimate the model's uncertainty about its generated text. High confidence scores indicate the model is more certain about its output, while low confidence scores suggest more uncertainty. Uncertainty method 2. Explain in detail. Depending on the specific Google AI model, you might be able to access additional uncertainty measures or use ensemble methods to estimate a model's confidence in its output. Challenges and fixes. Challenge 1. Explain in detail. Prompt engineering is crucial. The quality of the prompt significantly impacts the quality of the generated text. A poorly formulated prompt can lead to irrelevant or nonsensical outputs. A prompt asking for a summary of a complex scientific article without providing any context or background might result in a confusing or inaccurate summary. Provide clear and concise instructions. Include relevant context or background information. Use specific keywords and phrases. Break down complex prompts into smaller, more manageable parts. Challenge 2. Explain in detail. Limited control over model selection. The specific Google AI model used might not always be explicitly selectable. You might want to use a specific model for a particular task, but the available options are limited. Consult the Google Cloud documentation to identify the available models and their capabilities. Explore alternative LLM integrations within Langchain if the desired model is not available through the Google Generative AI interface. Challenge 3. Explain in detail. Potential for bias and factual inaccuracies. Like all large language models, Google AI models can exhibit biases or generate factually incorrect information. A model might generate text that perpetuates harmful stereotypes or presents outdated or incorrect information. Carefully evaluate the model's output for biases or factual errors. Use fact-checking tools or human experts to verify the accuracy of the generated text. Use the model's outputs as a starting point and refine them based on your own knowledge and expertise. Challenge 4. Explain in detail. Potential for hallucinations. The model may sometimes generate outputs that are not grounded in reality or contradict known facts. A model might create fictional events or invent non-existent entities when asked to write a story. Carefully evaluate the model's output for any inconsistencies or improbable claims. Use fact-checking tools or human experts to verify the accuracy of the generated text. Consider using the model in conjunction with other information sources to ensure the output is consistent with reality. Langchain Google GenAI LLMS Google Model Family. Description: the Google Model Family within Langchain Google GenAI LLMS provides access to a suite of Google's powerful language models, allowing users to leverage their capabilities for various NLP tasks. It's a high-level interface designed to simplify interaction with these models. Inputs. Model name specifies the desired Google model to use. Examples include text DaVinci 003, code DaVinci 002, text Curie 001, and others. Temperature controls the creativity and randomness of the generated text. Higher values increase unpredictability. Max tokens defines the maximum number of tokens the model can generate in a single response. Top limits the probability distribution of tokens to the top p%. Promoting more focused responses. Top selects the top k tokens with the highest probabilities. Filtering less likely outputs. Presence penalty adjusts the penalty for including specific tokens in the output, potentially encouraging more diverse responses. Frequency penalty modifies the penalty for frequent tokens, promoting less repetitive outputs. Outputs. Text. The generated text response from the chosen Google language model. Steps. Model selection. The user specifies the desired Google model. Input processing. The user's prompt is preprocessed and formatted for the model's understanding. Model execution. The chosen Google model processes the input and generates text. Output formatting. The model's output is post-processed and returned to the user in a readable format. Metrics. Perplexity measures the model's ability to predict the next word in a sequence. Lower perplexity indicates better prediction ability. Blue score evaluates the fluency and quality of the generated text by comparing it to human written references. Rouge score assesses the level of overlap between the generated text and reference texts, indicating the model's ability to capture key information. Visualization plots. Attention heat maps visualizing the model's attention weights during processing, highlighting which parts of the input text were most important for generating the output. Embedding projections representing the model's internal representations of words or phrases in a lower dimensional space, revealing relationships and patterns. Fine-tune parameters. Training data providing a dataset of text and desired outputs for fine-tuning the model's behavior to specific tasks. Learning rate adjusting the speed of the model's parameter updates during training. Epochs determining the number of passes through the training data during fine-tuning. Uncertainty methods. Temperature scaling modifying the temperature parameter during inference to explore different levels of randomness and uncertainty. Ensemble methods combining the outputs of multiple models or runs of the same model with different random seeds to assess the variance and confidence in the prediction. Challenges and fixes. Challenge 1. Model output being too short. The model might generate short responses, particularly when limited by the max tokens parameter. Sample use case that resulted in challenge 1 providing a prompt that requires a detailed explanation but setting a low max tokens limit. Fixes to challenge 1. Increase max tokens. Allow the model to generate more tokens by adjusting the max tokens parameter. Challenge 2. Model output being unclear. The model's output can sometimes be ambiguous or lack clarity, particularly when dealing with complex concepts. Sample use case that resulted in challenge 2 asking the model to summarize a lengthy article, resulting in a vague summary. Fixes to challenge 2. Rephrase prompt. Carefully reformulate the prompt to be more specific and provide context for the model. Use larger model. Consider using a larger model with greater capacity for understanding complex inputs. Challenge 3. Model output containing bias. Like any AI system, Google models can exhibit biases present in the training data. Sample use case that resulted in challenge 3 prompting the model to write a story about a doctor, and the output perpetuates gender stereotypes. Fixes to challenge 3. Use bias mitigation techniques. Employ techniques like adversarial training or debiasing methods. To reduce bias in model outputs, contextualize prompt include explicit instructions in the prompt to avoid perpetuating biases. Challenge 4 model output not being creative. The model might generate predictable or uninspired responses, especially with low temperature settings. Sample use case that resulted in challenge 4 asking the model to write a poem, but the output lacks originality. Fixes to challenge 4. Increase temperature. Experiment with higher temperature settings to encourage more creative and surprising outputs. Use different model. Explore different Google models with varying levels of creativity and fluency.